No, I'm sure we're all used to it with our Audible times 2, etc. Next, I'm going to hand over to a wonderful man who, again, has been here at every event I've known, Advenit Makaya from ESA. He's going to host the next session on technology transfer and use cases for space resources. Advenit.
Thank you very much, Lisa. Thanks for the introduction, and thanks everybody for coming. It's nice to see the conference growing. We have a bigger venue this year. Happy to host this session, which will start with Katriin Kristmann from Tallinn University of Technology. And Katriin will tell us about space-based solar power satellites manufactured on the moon from lunar resources. Katriin, the floor is yours.
Thank you for the introduction. Am I heard? Yes, okay. Thank you for the introduction. My name is Katriin Kristmann, and I am a PhD candidate at Tallinn University of Technology on a co-hosted research project with ESA. This is my third Space Resources Week, and I'm really happy to share this experience with all of us here. Today I will talk about the space-based solar power satellite that is manufactured on the moon from lunar resources. The space-based solar power concept has been widely studied, but interest in this technology has peaked recently. The emerging climate and energy crisis are pressing on Earth, and producing sustainable solar energy in orbit instead of on the Earth's surface would enable access to higher volumes of solar radiation and the possibility of constant solar energy production. However, a remaining major obstacle to realizing clean energy from space is the logistical challenge of launching hundreds and eventually thousands of rockets from Earth to deploy and build the solar power satellite. One innovative solution would be to manufacture the satellite components on the moon from lunar materials, thus mitigating the launch capacity bottleneck and the environmental impact. The lunar approach could decrease the necessary mass launched from Earth by 80% or more, and thus reduce the fuel costs and the related CO2 emission as well. The power produced in the in-orbit solar power satellite could also power operations in the lunar habitat. But our research group is focusing on the fabrication of the solar panels from the resources of the lunar regolith. And we focus on using pyrite or iron disulfide instead of silicon or other conventional materials as the photo-absorbing layer of the solar cells for many reasons. Well, first, pyrite or its elements are available in the lunar regolith. The recent Indian rover discovered sulfur in the lunar soil, thus predicting or confirming the predictions. Second, pyrite has significantly higher light absorption coefficient compared to other conventional solar materials. That way we can use much thinner layers of material in the solar cells. And third, pyrite can be treated at 500 to 700 degrees instead of 1700. So that's what we do. Our solar cells look like this. They are thin, lightweight, and flexible. You can take a closer look later with me. This is called the monograin layer solar cell, and the fabrication of pyrite monograin crystals starts with synthesis in quartz ampules in 500 to 700 degree furnaces. Then, after heating for several days, the crystals are removed from the ampules, washed, and sieved into narrow size fractions that are then used in manufacturing or fabricating the monograin membranes. Now, for the membranes, the crystals are embedded in a layer of epoxy or another polymer. The crystals are covered with a buffer layer or a p-n junction partner, if you're familiar with photovoltaics. and then covered with a front contact or a transparent front contact layer. The backs of the crystals are revealed by polishing, and the back contact is added. That's how we make these cells. And none of these steps includes any very expensive or complicated equipment. After making the solar cells, the rest of the solar power satellite components are manufactured also on the lunar surface, using lunar basalt for structural elements. Our research partners at Astrostrom are in charge of these steps, and you will hear from them later during the conference as well. The components are robotically assembled at the Earth-Moon Lagrange point 1, and the photovoltaics will supply at least 23 megawatt of power for lunar operations. We have put together a short film to illustrate our efforts on the lunar surface, from the mining and beneficiation to the fabrication of solar panels and completion of the solar power satellite. So please tune in to the short video, and we hope you can get as inspired as we are.
We are going to the moon to make monograin layer photovoltaics for solar power satellites from lunar regolith. Prefabricated, modular monograin layer photovoltaic factories will be delivered to the assembly hub at the Earth-Moon Lagrange point 1. From there, the factory modules will be gently delivered to the surface of the moon with a lunar lander gantry. After they have arrived, each module will be transported and added to the factory complex. Lunar regolith will be mined with razor mining robots. The regolith material will be delivered to the beneficiation and processing facility to extract iron sulfide and sulfur. Proper fraction of the precursors will be sieved out for further electrostatic separation. These materials will be synthesized into pyrite and further processed to produce monograin crystals. After the beneficiation process, the material will be delivered to the photovoltaic production facilities. Separated iron sulfide and sulfur, mixed with flux, will be added to the reactor chamber to grow pyrite microcrystals for the monograin layer solar cells. These will stay in the furnace for 7 days. Water will be added to wash out the pyrite microcrystals from the flux. Then the water will be recycled and a proper fraction of the microcrystals will be sieved out. Pyrite monograin crystals will be transferred to the roll-to-roll production line to form the monograin layer solar cells. This material will be used to fabricate state-of-the-art, lightweight, and flexible photovoltaic modules. The monograin layer photovoltaic modules will be transported with a lunar space elevator from the Moon to the assembly location at the Earth-Moon Lagrange Point 1. Here they will be robotically installed on the lunar solar power station. Once finished, this station will provide power for lunar operations to manufacture additional solar power satellite components for the Earth. Can you think of a better reason to go to the Moon?
Great. Thanks a lot. Thank you. And definitely come by the Astrostrom booth for a longer chat about this idea. Thanks.
Thank you very much, Katriin. And for the sake of keeping up with the schedule, we have time for one question. Yes.
Thank you. Hi, Robert Lindner, ESA. Can you tell us something about the efficiency of those solar cells using pyrite compared to, for instance, high-performance ones?
Excellent question. The reason why we all use silicon solar cells in our homes is because it's a mature technology with high efficiencies already reached. Pyrite is not at high efficiencies yet. The promised theoretical one is at 25, but no 25% solar conversion efficiency. But nobody, no research group has ever achieved that. So there is still a lot of work to be done in this regard. And we also haven't achieved that. So we are working with this in mind, and then one day.
Thank you. Yep, I think we will have to move on, unfortunately. Okay, one quick one.
Thanks, Katriin. Very nice presentation. I was just wondering, the solar panels will be in space exposed to sunlight, and I suppose the temperature will rise quite a bit. Silicon cells perform less well at high temperature. Do you think the pyrite cells would have like an advantage over the silicon cells, perhaps, in this regard? Would they perform pretty well, even though the temperature is higher?
But pyrite behaves very well in high temperatures. For the monograin approach, where we use these very thin layers, there is definitely the question of the supporting structures. Currently we use epoxy, and epoxy doesn't love high temperatures so much, but there are different polymers to be used. We will study the effects of the space environment more deeply, definitely in the future, but currently I would say that high temperatures, for the semiconductor, it's not pretty much okay.
Thank you very much, Katriin. We thank once again Katriin for presentation. And so in order to get pyrite or other resources, we need excavation systems, and that's the topic of our next presentation by Jonathan Slavik from Astrobotic, who will tell us about a propulsive excavation system for the Moon and Mars. Jonathan.
All right, thank you very much. Yeah, my name is Jonathan Slavik from Astrobotic, and yeah, I want to concentrate on a technology that we've presented in the past, some new information, some new testing results that have come out from this technology, but I also want to look at it in the context of technology transfer, looking at something that we were evaluating from a scientific perspective, new ideas that came out of that, and how those new ideas transferred into a technology. In this case, it's another moon excavation technology, but in this context, I think it's really interesting to look at how the scientific innovations and the challenges that we have to solve to do things like excavating resources on the moon can be spun out to other technologies, like Jerry was talking about with graphite electrodes being replaced with some novel technologies. This hopefully can be a demonstration of how that really can work. So yeah, I'm going to be talking about a program we call Rocket M, which I'm pretty proud of as an acronym, is a resource ore concentrator using kinetic energy targeted mining. But let's get into it. So first off, a quick obligatory slide about Astrobotic. I'm sure a number of you are familiar with it at this point. We had our first lunar lander launch earlier this year. Unfortunately, ran into some issues with some of the components on the vehicle. We were able to get out to lunar distance, but we're not able to land on the moon, unfortunately. But we were able to prove out a lot of technologies, get a lot of people spaceflight heritage with their technology. And then once we were out there gathering data, we made the difficult, but I think ultimately correct decision to actually do some very difficult work to get control out of our vehicle and deorbit it back into the Earth so we could be good stewards of the cislunar environment and give all future missions a better opportunity for success. And then we're ideally, hopefully this year, going back with Griffin to do the Viper prospecting rover. But the group I'm working with and representing today is our propulsion and testing group. We've got a very long history with vertical takeoff and landing rockets, and that rocket item will become a theme later in the presentation. So we've been flying those rockets for a long time, and as part of developing a lot of rocket technology, we have a very fun and interesting tech development program where we're creating a lot of really interesting technologies. And you might see in the bottom corner there, we've got rocket mining as one of them, and that's a system we'll talk about today. So mining on the moon. I think this is probably one of the few groups that I can give this presentation to that I don't really need to make a strong justification for why are we mining on the moon and why is it hard. But obviously things we've talked about, benefits to down mass, living off the land, using those resources in situ. And a little bit of a teaser here to one of the main resources we're looking at is water ice on the moon. This illustration here comes courtesy of our friends at Colorado School of Mines, and particularly Dr. Cannon has done a bunch of work characterizing what are the different forms this ice can come in. And that for us presents the challenge of mining it. You know, regardless of what form we find the ice in, we still need to be able to extract it. So, you know, talking to people in the construction and mining industry, everyone wants to just drive a bulldozer onto a starship, land it on the moon, get going. Even if we can do that, you know, there's addressable issues, right? System mass, power requirements, these, you know, we can use exotic alloys, we can get power requirements down, that's fine. But there are some open issues that terrestrial mining analogs just really don't address. And this is something I've beat the drum on before. Hopefully I can give a little bit more validation to it today. But the issues of maintenance and tool wear. I really like this image in the bottom right because it shows the digger teeth for excavation, right? You've got those teeth on the digging bucket that get replaced. On Earth, you know, you come in when they're worn out, you come in with a cut-off wheel, cut them off, weld on some new ones, good to go. When we're on the moon, that's going to be significantly harder to do. We're not going to have the highly refined tool steel alloys that we're going to be able to weld on there, and finding someone to come out there with a cutter and a welder is going to be quite the challenge. So how do we address these open issues of maintenance, tool wear, and something we'll touch on in a moment, beneficiation, that are real challenges that don't directly map from terrestrial analogs? Well, I think the answer is rocket mining. Using the exhaust plume energy from a rocket engine to actually excavate both bulk regolith, volatiles, and solid water ice out of the lunar regolith. So we won't dwell on this. I'll give a little bit more background on what those images are. So the idea is that we're going to mount a very small rocket engine onto the bottom of a rover, and we're going to be able to drive that around various areas on the moon, put down a collection dome, and fire the rocket into it, and all of that ejecta is going to come out and get captured and beneficiated out. I think one of the advantages conceptually of this is that all of the resources that we're looking for are pneumatically transported. And people in the mining industry may recognize that as one of the ways that you actually need to transport your material. Digging out regolith and resources just in a vacuum is not necessarily all you need to do. Once you get to a refining step, it's usually transported pneumatically or hydraulically, which is not just naturally going to happen on the moon as it does on Earth. So this situation gives us a carrier gas for these materials to be beneficiated. So this initial concept and why I consider this a technology transfer, this initial technology came from looking at deep cratering plume surface interaction testing. That's where we're firing rocket engines at lunar regolith simulant, Martian regolith simulant, and looking at how they behave at different distances, at different thrust levels, mainly to provide anchoring data to computational fluid models that are looking at how ejecta behaves, and we can simulate it. We run those models with terrestrial parameters, and then we actually test terrestrially to see if those models are accurately simulating what happens. And one of the things that you'll see is as you get the rocket engine closer and closer to the surface, you stop scouring the surface, you start digging a really deep hole. And this concept of, oh, this plume digs a really deep hole was combined with another thing that we observed during some development for re-entry ablatives, where we sort of the core of this idea came from, we were having fun over Thanksgiving in the US, and we decided to try and cook a turkey with a rocket engine. And as it turns out, I'll spare the video because it's a little gross, but as it turns out, you don't end up with a cooked turkey, you end up with a widely distributed, very cold turkey. And it makes sense if you've been exposed to the propulsion world at all. A rocket nozzle takes the extremely high pressure, high temperature condition of inside a rocket chamber and ideally converts it all to kinetic energy. So a rocket plume, while it is technically hot, is mostly comprised of kinetic energy. So combining this, oh, it's mostly kinetic and it digs a deep hole, we were able to pull together these disparate scientific ideas and say, let's turn that into a technology. So the initial proposal, it was put out for a NASA Break the Ice challenge. And really a lot of the work that went into this was saying, let's assume that this technology works, which is a big jump. And let's look if it even makes sense to develop this. So a lot of work was put in to evaluate, where can we go, where are these sites where ice is valuable that we can both extract the high concentration water ice, or what we suspect is high concentration water ice, and bring it back to a location where it can be beneficiated in a pilot plant or be useful somehow to a mission. So a lot of this work was evaluating, does this make sense? Can we do this at a scale which would make sense on a reasonable size lander in a reasonable time frame? And we tended to think it's going to work, but we were also going off the assumption that rocket mining actually works, which is quite a big assumption. The QR code here is to a longer form video. It's a little too long for this forum here, but I encourage you to take a look at some of that previous work. Give some good explanation of how the system would work. So after that, once we decided that this is a useful technology to go after, we applied for a phase 1 SBIR to build out a physical prototype, see if we could actually do this. So this is sort of the new work that's being presented here. The first real challenge is saying, can we actually put a dome onto the surface and liberate all of the regolith and volatiles and ice solids and everything and actually get it to stay in there without it just blowing out the sides? So we started doing a lot of that development with the seal geometry and engine configuration with just nitrogen cold gas testing, looking at if we could get it to stay in. And we actually were able to develop a pulsed system where we're looking at subsurface pressure data, where we're looking at the speed at which the pressure rise from the induced gas travels through compacted regolith, and we're able to look at the individual timestamps of when that pressure wave arrives and long story short, we were able to figure out a way to make it work. So the next step was, well, we have to fire a real rocket engine into real regolith and figure out if we're collecting anything. Now, we were on a pretty short timeline, short budget, about 100 grand and 6 months. So that's it's not a lot of time to make a prototype if you've ever done hardware development. So what we came up with was saying, well, let's just see if we can capture some of the regolith and that's being liberated from this plume and deposit it in a tray, and then we're just going to eject the gas. We'll worry about gas collection in the next phase. So we built this this prototype here that we were able to put a rocket engine on top of, and then a tray that would collect the regolith as the gas went through a tortuous path on its way out. So yeah, it was a little rough and tumble in terms of a prototype, but we're ultimately just trying to prove that this idea holds water. So another thing that was really interesting and that came up, and I think is a core aspect of the Break the Ice Challenge, some of the work that Dr. Cannon is doing, is looking at, we don't know what form water ice is going to be in, right? We have indirect measurements from LCROSS, from LRO, looking at indications that water ice is there, but is it cemented? Is it discrete? Is it agglutinates? Like, we don't really know. Until we get up there, Viper starts drilling holes, we don't know what's going on. So in order to test that this is viable, we went to 3 different situations. We went to dry regolith, we went to discrete ice fines, and we went to cemented regolith, and fired into all 3 of those. Now, our simulant was not as high of fidelity as some of the work that I've seen people in this group doing, but again, we were just trying to prove it out. So we were doing 3% water by mass, ground up fines, and we're able to actually create a layered water fine structure. And then in some of these pictures you can see we also just poured in liquid water and then sprayed it with a bunch of liquid nitrogen in order to freeze it to create cemented regolith. And then to address one of the other main concerns that people have brought up is, aren't you just going to melt everything? Aren't you going to volatilize all the ice around what you're trying to collect? So to look at that, to see if that's true or not, we put some subsurface thermocouples at varying distances away from the actual plume collection area to ensure that we're not introducing too much heat into the environment. And the results were success. We were able to fire the rocket directly into all the forms of frozen regolith that we had around, and even with this extremely rough analog prototype that we were doing, we were able to collect 4 times as much water in terms of mass as propellant mass was used to extract that water. Now we think with a little bit more efficiency we can get up to the 8-9 times as much, but hey, we're at least proving in like the roughest worst case scenario we're still mass positive. And what was really interesting about this is we actually collected solid ice chunks in the collection tray. So that really proved out our theory that the kinetic energy of this plume really goes into moving the regolith, moving the ice, not melting it. So yeah, our thermocouples outside of the plume area showed no temperature rise, and even when we were out in the desert in California, it's somewhere between 30 and 40 degrees Celsius out there, we were able to rush out after we had safed the rocket engine, open it up, and find solid ice chunks in the trays, which was pretty exciting. So yeah, it was just a really validating thing to say, wow, this is a technology that came out of some unrelated scientific investigation that we can ultimately transfer into a useful technology. So it was really interesting, and we're really excited with the results. So the next steps really are looking at both the beneficiation. We have to functionalize the cycloidal and magnetic separation system. We were baselining a system called Aquafactorum that was proposed by Dr. Metzger out of Florida, but there could be other systems as well, and then looking at getting deeper, going to a higher fidelity sample here. But I think what's really interesting is looking at all the ways that a new technology like this can enable different types of extraction. There's been a lot of conversation around helium-3. This is a technology which can extract volatiles without having to worry about trying to trap those volatiles as they're disturbed from the regolith, or trying to have some exotic capture mechanism, because it's built into this extraction technology. We've also looked at this for doing deep boreholes for prospecting on the moon, Mars, other applications, and sort of looking at how do we incorporate excavation and beneficiation into a single step, I think is really important in improving the efficiency for terrestrial excavation technologies. So with that, I'm pretty close to the end. We might have time for one question, but thank you very much for listening in.
Thank you very much, Jonathan. Very good insight into turkey roasting capabilities. One question, Bernard.
Bernard Frank from Eurospace Hub. So could you have a hydrogen oxygen rocket that you refill with hydrogen and oxygen you extract from the ice? So what would be the cycle efficiency of doing that?
So yeah, that's something I didn't necessarily get into, talking about doing a hydrogen-oxygen rocket and what's the efficiency. So in our first system, we showed that the propellant mass to extracted water is about 4 to 1. We're hoping to get that closer to about 9 to 1. But you would still need some amount of energy to split that water back out into hydrogen. And that is notionally what our plan is to do this as a hydrogen-oxygen rocket. It has other advantages like having easier time igniting and things like that. But the goal would be to use about 10% of that, re-break that down into hydrogen-oxygen and keep that as a closed loop going within the system. We'd also want to use that hydrogen-oxygen, since we have it available. If we're able to produce that at a pilot ISRU plant, we'd be able to run the system on fuel cells rather than solar alone. So we'd be able to have a very high energy density working with chemical energy storage rather than just electrical.
Yeah, thank you.
Thank you very much. Thanks, Jonathan.
Yeah, thank you.
So, Astrobotic is a very good example of a private company looking into ISRU technology, and that's the topic of our next talk, which will be online. It's by Madison Feehan from Space Copy, and she will tell us about exploring early pioneering private sector technologies for ISRU and lunar manufacturing.
Sorry about that. I guess somebody didn't tell me my microphone was on. Apologies. Hello, everybody. It is an honor to be joining all of you here today. My name is Madison Feehan, and I am the founder and CEO of Space Copy. To introduce myself briefly, I've been working in the space industry for a few years as an employee of NASA, studying advanced lunar instrument development with a background in commerce. I also serve as the co-founder and CFO of a wonderful lunar mining startup called Moon Trades, and as the G100 Region Chair of Space Technology and Aviation for the province of Alberta, Canada. Today, I'm here to demonstrate to each of you what innovation in space and how the commercial space industry is shaping up to be the next leader in utilizing space resources to support the global mission of going back to the moon. Presenting my talk on exploring early exploration for private sector technologies for ISRU and lunar manufacturing. Next slide, please. The usability of space resources through in-situ resource utilization processes boasts a revolutionary approach to lunar colonization as we know it. I will attempt to balance my talk today between history and the future, and as many brilliant researchers globally have concluded, the value of space resources as a commodity has not been thoroughly recognized enough. The value of regolith-based commodities extends itself to include supply chain management for sustainable infrastructure development, extractable resources for mining, processing, and manufacturing, as well as the application of lunar resources towards clean energy and off-world agricultural projects. Lunar regolith as a standalone material, well, it's able to maintain an angular or vermicular shape with variable particle size distribution according to its location, either highlands or mare. Some of the discussions today highlighted that despite the challenges, however, of working with these resources in their raw form, it is possible to beneficiate these materials for the production of various supplies and structures. The composition of regolith is both abrasive and bearing the properties of being electrostatic, of course, due to the harsh vacuum environment and characteristic lack of atmosphere exhibited on the moon. Now, despite this, the high silicon oxide ratio of regolith makes its behavior recognizant of ceramics, which have been employed for commercial additive manufacturing since 1986. Now, coincidentally, this was also the same year that the earliest forms of regolith manufacturing were being explored by private and government entities in the United States. Next slide, please. For the particular applications of regolith manufacturing at Space Copy, we utilize material as a feedstock for a multi-process laser powder bed fusion that operates in a vacuum and is capable of defining the mineralogy of regolith samples. We use advanced Raman spectral lasers, followed by a precise refinement and beneficiation of particles suitable for selective laser melting applications, and all autonomously controlled by custom-trained algorithm systems, those of which are controlled in part by robotics and deep neural networks. Our technology also extends itself to extrusion-based printing adaptations, as well as subtractive technologies like casting, according to the parts being printed and their intended purposes. Next slide, please. Some of the benefits that I do like to highlight about Space Copy's technology in particular include its custom optimizable process parameters. Now, this allows for precise printing of really complex geometries, and that's not something that you've seen historically in additive manufacturing, especially of regolith. Now, we range from larger infrastructure, such as interlocking bricks for habitats and roadways, heat shields and industrial piping, and then transitioning down to the smaller repair parts and precision tooling fabrication. Our patent-pending systems leverage machine learning and computer vision as part of its core technology to have the option of autonomously operating in extreme environments. This, of course, as has been discussed broadly today, is important for technologies in space to be applicable on Earth as well. And for Space Copy, our applications for defense in environments like the desert and Arctic, as well as in space, for use in reduced gravity environments with high levels of radiation and temperature extremes, characteristic of the kind of southern polar region of the lunar surface, are just some small parts of what makes our company and so many other startups in this ecosystem of mining and manufacturing so important. Next slide, please. Analyzing this technology and similar robotic mining and manufacturing systems that are currently being developed, the scientific and economic value is clear. Space Copy, for example, boasts numerous practical applications for deployment in extreme environments on Earth and in space. Now, terrestrially militarized applications of this hardware directly translate to infrastructure development in areas like combat zones and natural disaster areas, where lunar and Martian applications of the same technology can extend to the production of infrastructure for Artemis. With direct connection to government, industry, and academia, the utilization of space resources with 3D printing has been widely studied, in particular, like projects such as ESA's EAC Luna program. And further to this, it's broadly recognized for being a central technology for in-space servicing, assembly, and manufacturing, slated to be valued at a total addressable market of over 6.9 billion euros by 2030 alone, just for lunar manufacturing. It's incredible to see. Next slide, please. Now, to characterize this for all of you in a bit of a more realistic sense, what you can see on the presentation is an active demonstration of the technology that myself and my team at Space Copy are actively producing, with the use of lunar simulants that bear properties with similar geotechnical characteristics to Apollo 17 soil. Now, I want to stop and take a moment and explain the importance of utilizing this specific regolith simulant. Now, Apollo 17 soil is known to be rich in titanium content derived from ilmenite, and that generally allows for easier adhesion of particles when doing the actual additive manufacturing. Now, given that Apollo 17 regolith is also the world's closest currently studied relative to the South Polar region, it is easily demonstrated that Space Copy and many other technologies that are using similar simulants are working towards specifically addressing many of the unknown variables that lunar manufacturing carries with it. Our next phase will be to use a custom developed simulant, especially for us, to test optimized parameters for sintering and melting. While we currently focus most of our operations out of Canada and the United States, we are also excited to be expanding our role throughout Asia and Europe greater. While we are currently focused on printing more complex geometries and testing in a lunar analog environment later this year with some of our coupons, this kind of initial proof of concept that you see here is essential to realizing the capabilities of additive manufacturing with ISRU. Now, if you take a moment to think about the economic benefit, it's calculated by Research and Markets that ISRU through additive manufacturing is currently able to reduce upwards of 70% of resupply payload mission costs. 70%. That's over 4.6 billion euros of cost savings per astronaut within the first operational year of Space Copy's technology on the lunar surface, allowing this capital to be reinfused back into local economies and, of course, back into the grand science community that is pioneering so many incredible technologies similar to this that will really be responsible for being part of the core framework system that our entire lunar economy will be built on. Next slide, please. Now, I want to take a moment and broadly summarize that the priority here for each and every person within the space community is to set a precedent for how we sustainably colonize the moon. And the very audience in this room, whether in person or online, we all have the privilege of defining how this framework would look for future generations. We get to be the people out there who say, this is how it's going to be for space, and this is why, because we need to do it responsibly and sustainably. For the privatized technology development of lunar hardware that utilizes space resources, we at Space Copy imagine a closed-loop and circular lunar economy that relies on material extraction, beneficiation, resource use, manufacturing, and of course, infrastructure development. And we require the support of the local space community and the global space community to take our work to the next level. We're very excited for our next couple of phases coming up. We're heavily focused on research and development right now, expanding our partnerships globally, working with some great laboratories across the world. But we are truly at the beginning, and this is a very great juxtaposition between space resources and actually having commercializable technologies, especially from small businesses, to recognize the importance and the need for new industry stakeholders to enter into this game and to give us a brighter, broader future than we could have imagined just independent of academia or just government. We now also have these industry leaders taking hold, and we are proud at Space Copy to be part of that. Next slide, please. I want to thank you all kindly for your time and attention to this conversation, but more specifically to the subject matter itself. We are at such a crucial time as industry leaders to be able to characterize how this new framework of space resources is going to work. Now, for any further inquiries about Space Copy, please visit spacecopy.com, or for Moontrades, if you're interested in lunar mining, that would be moontrades.org. And please feel free to scan the QR code or take a picture of that final slide, and a member of our team will look forward to following up with you. Thank you very much.
So we will not take any question for online talks. You are free to contact Madison through the QR code or her email address. And we move to the next speaker, who is Jehn from the Colorado School of Mines, who will tell us about a very important topic on landing pads, so site preparation and landing pad performance requirements for a lunar human landing system. Jehn.
I also think this is a very important topic. Okay, so I'm Jehn. I'm from Colorado School of Mines. Just some background and information about me and my credentials. I am a licensed civil and structural engineer. I have about 10 years of experience in terrestrial design. I've designed things from residential construction to high-rise construction in high wind and high seismic environments. I'm also a PhD candidate in the Space Resources program at Colorado School of Mines. My dissertation is focused on geotechnical and structural technology development. I'm calling it regolith structure interaction, but basically lunar surface construction and foundation development. So this presentation is focused on establishing the requirements and kind of a design methodology for a lunar landing pad system, particularly one that can resist loads coming from a human lander system or an HLS, and I'll describe what class of vehicle that we're going to be designing to here in a little bit. So there's a lot of technical information involved in this, and I'm trying to fit it all within 12 minutes, so if you have more questions, come talk to me afterwards so we can talk about landing pads more. So to begin, I just want to quickly review vertical takeoff and vertical landing technology. So VTVL, vertical takeoff, vertical landing operations, refer to a technique in which a rocket takes off vertically from a launch pad and then also lands vertically back on the ground or another designated landing zone. And these are the operations that are going to be used for the lunar surface. I have a figure on the left showing typical operation where the descent trajectory, the vehicle slows down and then reorients itself vertically and then approaches the ground to the surface, and then the engine will eventually cut off and then it will free fall that remaining distance. So there's a lot of interactions with the surface in this operations, and that's what we're going to be designing for. So at this point, I think we're all pretty familiar with this type of operation, particularly with SpaceX reusable rockets. I've shown there on the right a Starship HLS that uses this type of operation, and this will be a rocket that's going to be selected for Artemis 3. So I'm glad John went before me because he had a really good example of why rocket plumes can be detrimental to the surface. So I'm actually not going to talk about this slide a whole lot, but I will say that that figure on the left indicates a model of a medium-class HLS lander. So you can see that some of those gas particles can reach a speed of up to 3,000 meters per second. So yeah, those particles interact with the surface, create ejecta, and that's a problem. This can damage the actual engines of the rocket or the structure, and then actually anything in the surrounding area of that rocket surface interaction. So in addition to the rocket interaction, there's also, when the vehicle touches down on the surface, it can actually deform that surface or settle. And this can cause the vehicle to either tilt or even fall over. So this is going to be important to kind of create a surface that can mitigate these problems. So before any significant mass can be landed on the surface, a stabilized landing zone should be provided. So this is basically accomplished by preparing and compacting an indigenous regolith surface and then constructing a durable engineered surface material on top. So that's what's called a landing pad, or what I'm calling a landing pad. So the design of a landing pad, basically the anticipated loading parameters need to be addressed. So I've organized them here into two main categories. So there's environmental design parameters and then external loading parameters. I think we're all pretty familiar with the environmental differences. The lower gravity, lack of atmosphere, extreme temperatures, solar heat flux, radiation exposure, micrometeorite impact, and actually even seismicity. So for this analysis, I'm actually only going to summarize the external loading parameters, which are those induced by the vehicle itself. So for those parameters, there's the vertical and horizontal pressures produced by the rocket exhaust. There's also high temperatures and heat flux resulting from those rocket plumes. And then there's impact from the lander legs. And then finally, after it lands on the surface, there's a static bearing force of the stationary craft. I'll note that there's two other loading conditions that come from the external loading. One of those is the vibrational loading caused by the acoustics. So acoustics can actually be transmitted through a transient atmosphere created in the rocket plume itself, and those can vibrate the surface and cause issues. But I've noticed in many of my analysis that these loading conditions don't actually govern. It's actually the pressure that causes is the governing load case. So I'm not going to include them in this analysis. And then there's also the final loading case is the vehicle loses control during landing operation and actually impacts the pad. So this is going to be a really extreme load case. It's going to require a really hefty pad to resist these, so I'm not going to include those. It'll likely not be the first landing pad constructed to resist those loads. So a landing pad system will resemble what we call a slab-on-grade system terrestrially. So the image on the right indicates kind of a load path for such a system. So slab-on-grade is simply a thick wearing surface supported by a subgrade. For a lunar landing pad, this means that it'll be a prepared and compacted regolith surface supported by a sintered regolith pad material. So this is leveraging ISRU for all of the components. So the needed material properties for the pad system are the compressive and tensile strength of the sintered material, as well as the coefficient of expansion. And then for the subgrade and subsurface preparation, there will need to be clearing, grading, and compaction of that surface. The analysis I'm about to present assumes that it's already been cleared and graded, so I'm only going to present minimum requirements for the compaction levels. So this figure basically shows the model setup that I used in my analysis. So I've created a circular landing pad supported by a regolith subgrade paired to various compaction levels. You can see that the lander that we're going to use is just going to descend towards the surface directly in the center. And then the analysis was conducted to determine the minimum material properties for both of these, both the surface and the regolith below. For the loading, I'm actually going to utilize estimated data based on Blue Origin's Blue Moon HLS. So this is a medium class lander that's going to be expected to be used for the Artemis 5 mission. So it seemed like a pretty good candidate to run this analysis on. Plume data for the Blue Moon is not publicly available. It's extremely proprietary, and plume data is difficult to come by. So I've actually scaled the loads based on available data from CLIPS landers, and then I scaled it up to the higher mass of what we're expecting. So this slide just provides a summary of the loading conditions that I applied to the model. Just to summarize real quick, vertical pressure is going to be about 18 kilopascals at the maximum and dissipate outwards. And then the estimated temperature at its maximum is going to be about 4,000 degrees Celsius, and then dissipating outwards as well. There's also going to be static forces from the lander legs. There'll be a concentric and eccentric landing condition. So concentric is all 4 legs touch down at the same time. Eccentric is 1 leg hits first. So obviously the 1 leg that hits first is going to be the higher loading case and will likely control the design, which it does. So spoiler alert. Okay. So there's 4 general failure modes that I've determined in this analysis. There's 3 failure modes specifically for the pad material itself, and then 1 failure mode for the regolith. So starting from the top left, we have a bending failure from the plume pressure, and then the figure below that is the expansion upward and outward caused by the increase in temperature from the plume. This can actually even create a spalling effect as well. And then there's a punching shear failure, which is a top right figure. That's when that leg actually punches through the pad material. And then on the bottom right, we have our regolith surface failure. So this is the vertical settlement failure of the underlying regolith subgrade. And you can see that the pad is actually sinking down into the regolith surface. Okay, so let's talk about the results. We're going to start from the ground up. The compaction of the regolith subgrade, I produced a geotechnical model. This is a one-dimensional deflection analysis. So this is to analyze the anticipated settlement based on a specific compaction profile. So I've assumed a rigid pad material that distributes the load outwards from the plume and the lander legs themselves. So in this figure, I've produced a maximum anticipated settlement based on 5 different regolith profiles. There's a non-compacted state, that's that line on the far right, that's the black line, and then compaction to 60, 70, 80, and 90% relative density as you move left across that figure. So the points at the top of the graph indicate kind of a maximum anticipated vertical settlement of the regolith. So if no compaction is done before the pad is constructed on the surface, there's roughly 9 centimeters of anticipated settlement. If you go to 90% relative density, the far left line, you can reduce that to about 1.7 centimeters. So if you're interested in this analysis, I actually published a paper in last year's AIAA Ascend conference that goes through this whole analysis. So it's also worth talking about the bearing capacity of these regolith profiles. So this figure shows the relative density profile on the x-axis, and then the corresponding ultimate bearing capacity on the y-axis. So I've highlighted the bearing pressure of our lander in red. As you can see, it matches up to about a 50% required relative density, so before surface failure occurs. So there's really no concern for a bearing capacity failure, and all we should really be concerned about is mitigating that settlement. All right, so let's talk about the pad itself. So I've summarized the demand capacity values here. So the values highlighted in orange are actually the controlling load cases. So I've assumed a structural material property based on a sintered regolith, which is from a paper titled The Structural Assessment of Unrefined Sinter Regolith Simulant, and I've actually noted that here on the bottom left. So this provides estimated material properties for the sintered regolith. But basically, to summarize, there appears to be no problem in compression of the pad material, and the behavior of the pad is actually completely controlled as a tension-controlled failure system. So basically, that just means that the demand capacity ratio for tension versus compression is the tension is higher. But it does seem that the sintered regolith material appears to have enough tensile capacity to resist these forces. And this is to resist that upward and outward bending that I talked about earlier. The pad thickness was actually governed by that punching shear failure that I talked about. So after conducting a punching shear analysis, I've determined that a 15-centimeter pad appears to be sufficient to resist the loading from those legs. So based on the full analysis, I've provided a summary in detail here. So again, it appears that a 15-centimeter pad, or thick pad, can resist the anticipated loading. I've suggested that the pad actually taper on the thicknesses of the edges. This is to provide additional regolith stabilization outside the plume effect area and also decrease the construction costs of that area. Based on the settlement and mitigation analysis, I believe that 70 to 80% relative density will be sufficient to limit this construction, or to limit construction costs. So for the 70% relative density, this basically means that we would need to compact the surface basically 4 centimeters below the native regolith surface, and that would, before that relative density is actually naturally achieved. So this would witness about 5 centimeters of overall consolidation settlement. If we were to choose the 80% route, that means we would have to prepare 6.6 centimeters down, and that would reduce our settlement to about 2.9 centimeters in consolidation settlement. Okay, I'm just gonna wrap up here, but I'm gonna end with a quick plug. So this analysis and procedure is, and the design methodology behind this are also being used to help develop what we're calling the Lunar Infrastructure Engineering Design Analysis and Construction Guidelines, or LIDAC for short, which are being written by the American Society of Civil Engineers. Within this guidelines document, there's gonna be a lunar structural loads chapter that I'm helping to draft. Within this section, there's a whole section dedicated to rocket plume loading, which will help provide minimum loading conditions for landing pad design. And we're gonna actually be having a special presentation on the updates from these guidelines at the upcoming Earth and Space Conference, if anyone else is gonna be there. It's in April in Miami. And with that, I am gonna wrap up and welcome your questions. And I know that these are clickable links and that's not helpful to anybody, so just come talk to me afterwards.
Thank you. Thank you very much, Jehn. So for a change, we'll take the question online. So Fyodor Sergeyev is saying, so according to what you presented, it's not possible to take off and have an emergency landing at the same spot on the same pad, or is it?
So those loads are based on landing loads. So takeoff loads are going to be different. That's going to be much closer to the pad, and that would require a different design approach. Basically, it's going to be a thicker pad.
Thank you very much, Jehn. And to wrap up with this session, we'll move to our next speaker, Daniel Sachs, from the Canadian Space Mining Corporation, and he will tell us about the commercialization of dual-use ISRU technology. Daniel.
Thank you. First off, thank you to ESA, to the Luxembourg Space Agency, to ESRIC for giving me this opportunity to be here. It was a great conference and great to see a lot of like-minded people following some very solid presentations, definitely more technical than mine, so this will be a little bit different. I think we were asked to talk about dual use, and you know, for us, dual use is more than just one tech. It's the entire ethos and being for the company. So yeah, so who are we? CSMC is really an infrastructure company. That's how we like to think about it. That we solve long-term problems in space related to lunar habitation and lunar settlement that address immediate challenges on Earth. So everything is about dual use, and we do that in 3 verticals of the company. First is resource utilization, second is energy, and the third piece is healthcare. So company founded by myself, background in real estate development, Richard Boudreau is our chief scientist, very varied background, world-renowned physicist, repeated 13 times entrepreneur with 7 exits, and expertise across quantum, nuclear, metallurgy, 100-plus patents. Mark Donato is our head of engineering and ran MDA for about 40 years. Mark's the guy who ran the Canadarm and RadarSat projects. Adam Greif's our CEO and COO, background in robotics and healthcare again, and then Dr. Andrew Feustel, Drew Feustel, who was chief astronaut at NASA before, as well as geophysicist, and we have a deeper team, about 10 people right now, or 11 as of this morning, and going up to about 15 by probably middle of this summer. The Canadian Space Agency has identified 6 areas of future space exploration leadership for Canada, particularly around the moon to Mars kind of viewpoint. And I founded the company about 3.5 years ago, and we've carved out a dominant position in 3 of those areas. So we've won 4 contracts with the CSA over the last really 3 years. We've been doing. They can't quite hear you online. So. Oh, they can't hear me online. Okay. This is easier anyway. Does it work? Okay. So we have won 2 contracts in the ISRU area. We spent a year working through a plan for Canada to build world-leading space mining and space resource industry as international partner for the rest of the world, and did that work. And then we've moved into prototyping of a ISRU process that we've developed internally, a metallurgy process for production of oxygen and hydrogen. There's some other dual uses around that, and we can get into that in a minute. Then on the energy side, we're developing a nuclear reactor for the moon. We have one of 5 contracts on the planet to develop a nuclear reactor for the moon, competing against Lockheed, Westinghouse, Rolls-Royce, and others. We're definitely the David and Goliath in that scenario, but very happy with our position and confident that we can beat all those parties by several years to the moon. Then on the healthcare side, not traditionally thought of as part of space resources from us, it is adjacent infrastructure and kind of base layer infrastructure, especially as you're thinking about extensibility from Moon, Mars, and longer duration. And we developed a shipping container hospital for the CSA there that we are working to implement as a dual-use technology. I think I have a little video here to show.
Technology designed for space has a long history of benefiting life on Earth. From the GPS that you use to find your way around, to the Velcro on your kid's shoes, space technology has enriched the fabric of our everyday lives. But technology for space shouldn't just be for the future. It should help solve today's problems, like healthcare in the most remote parts of our country.
With the financial support of the Canadian Space Agency, CSMC has developed a purpose-built, medically customized capsule that will deliver care to the most remote corners of Canada and beyond.
As humans extend our reach into the stars, Canada wants to become the global leader in space healthcare. The Connected Care Capsule is a prototype that will be used here on Earth as a capability-building exercise towards the creation of a hospital that can function on the Moon or Mars. CSMC is an infrastructure company focused on solving big challenges in space by first solving problems here on Earth. And when we can deliver care in places where resources are scarce, we are paving the path to deliver care beyond our borders and inspire the next generation of Canadians.
So C3 was a great example, I think, of dual-use tech. We developed it for the CSA as a prototype. That was about a month to design it, 3 months to construct it, and 3 months to test and deliver. We did that on time and on budget. And then we're moving immediately to commercialization for that. So we developed it as a TRL-4 technology for the CSA. We also developed it as a TRL-9 technology internally. And we're starting to build pilot projects, and we hope to build 100 of those over the next kind of 7 years and deploy them into the Arctic and different remote areas where they can help people. So just in terms of like philosophy, I think we are a dual use company. I think dual use is key. It makes good business sense. It also motivates the team. I think it's not only the right thing to do, but it's a smart thing to do. You know, Earth is the bigger and better rock. The moon is a great rock sitting out there in space, but it is not as nice a rock. Earth has a much larger population and is therefore a much larger market. I think for every single thing we look at, you know, and maybe I'll take some flack for this, but I think the economic viability of anything right now that is on the moon is non-existent. I think it's nice in edge cases and in terms of testing, but the moon becomes a viable market in, let's say, you know, 7 years. The timing is uncertain, and so I think thinking about dual use is a way to both hedge risk from a business standpoint, as well as to retire risk along the way, to develop these technologies, continually refine them, create a R&D feedback loop that allows you to perfect these products and really be strong by the time you get to the moon, to think of them at parallel path. You know, it feels good to do dual use tech, and I think it is important. You know, we have a lot of problems on Earth. It motivates the team to work on solving these problems and seeing them in a real way that they can address these challenges that we have. I think that is really a key piece for us. So in terms of resource technologies, I'll maybe just walk you through some portfolios and how we think of dual use tech. So we have a couple sensors that we're developing for resource detection in the lunar environment, one that's surface-based, one that is space-based. Again, you know, for all of those, the market is huge and full of potential in the lunar environment. It is much bigger on Earth for all of them. Whether the markets are civil engineering, resources, defense, all of these technologies fit as dual-use technologies today, and we see that as the immediately viable market to be prepared for. Then we have a process called Hydra Plus, which is our ISRU process that's been funded by the Canadian Space Agency and is in bench scale testing right now for extracting volatiles from the lunar environment. And we are already working on and have unlocked some new funding to be announced from other groups for commercializing those as a dual-use technology on Earth, applicable immediately to mining and metallurgy on Earth, where we see some great economic potential from that, and potential to do good as well, to make more environmentally friendly materials. On the energy side, on the nuclear side, we're developing a microreactor for the lunar environment, and you know, the lunar environment is a key piece. We believe that nuclear is the gating factor for ISRU. I know you may be technology agnostic, but it produces thermal energy in a really efficient way, and also has some lunar night survivability facets that we think can enable the entire lunar environment. But again, the dual use on Earth is really also what drives us. So you have this ability to replace diesel power in the Arctic. The Arctic is heating up at 5 times the rate of the rest of the planet. That is going to kill the rest of the planet. And there's a lot of other problems related to diesel from a logistics standpoint in the Arctic, refueling of these communities, the spills that happen, and then the negative health outcomes. As our chief scientist, Richard, likes to say, someone had the dumb idea to place diesel generators on the western side of every town in the Arctic. And so they blow plumes of ash into the town, and that leads to all sorts of terrible respiratory outcomes. So there's a lot of reasons why we think that's good. Ultimately, we think we can sell maybe a handful of nuclear reactors for the moon in the next decade and a half, and we think we can sell 100 of them in the Arctic. So I think
again, it's another area where the terrestrial business is a bigger business. We can do good, and we can adapt these technologies. I think that's all I have. I'll just finish with this. Make no little plans. They have no magic to stir our blood. That's Daniel Burnham. He was the architect behind Millennium Park in Chicago and Flatiron Building in New York. And we're working on big things, and big things for a reason. Thank you.
Thank you very much, Daniel. Do we have any question in the room for Daniel on dual-use ISRU technologies? So I have one, Daniel. So you showed a couple of examples on how terrestrial application can serve lunar application. Do you have examples on the opposite?
Yeah, I think a lot of our technologies are taken and adapted from terrestrial technologies. So a couple of our sensor technologies are developed utilizing previous work that our team and our chief scientist had done. The terrestrial nuclear piece is a spin into space, let's say. And then, yeah, all of them have terrestrial ties to them in terms of spin in and spin out. It seems to be a two-way street.
Okay. Thank you very much, Daniel. So we wrap up this session, and the next one is in 15 minutes at 1600.